Testing, testing. Testing.
Testing, testing.
Yeah, that's for more than you just yeah, that's right. This is sort of before the student services run. Yeah, you think I can have it. Yeah, sure.
Is this on? Yeah, I'm turning it on. here. Can everybody online hear us? Give me a second.
Yeah, at some point.
There's some delay.
Oh, that's on the live stream.
So,
Okay, good afternoon. Welcome back to our afternoon session. Today, I have the pleasure to introduce Arkaitz Rodas. He's a good friend of mine. First time I met him, he came for an internship to JLab in 2018. Later, he got his PhD at Complutense University of Madrid in 2019, and he joined the College of William and Mary for a postdoc position that he currently holds. And he has the honor to become in October a new Nathan Edgar Fellow in JLab. That is the most prestigious fellowship on the lab. So he's going to tell us a bit about iron spectroscopy and, well, in particular, the quest for exotic hadrons. And, well, as we say, just don't be shy. You can interrupt at any time. If you have questions, just raise your hand. Same with our online audience. Just raise your hand in the Zoom, and we'll bring the questions immediately. So the floor is yours, Arkaitz.
thank you very much, Juan. Well, let me first thank the organizers for inviting me. I think this is going to be a cool set of lectures. So I'm very glad that you guys are very fresh, and this is the second day. You still have lots of energy. I hope not to drain you with energy and then instead of drain you, motivate you to keep looking at this. So at first I thought that I would give a set of lectures. It's going to be just 4 lectures, 2 today and 2 on Friday morning. I thought that we need 2 in them on the quest for Exotica. So basically talking about exotic mesons in particular. Then realize that you don't have, you have introduction to QCD, you have introduction to small x and to a perturbative expansion, and you don't have an introduction to particles in general, so I don't know what the backgrounds are. And I thought of doing something very trivial kind of for the first couple lectures, so we all are on the same page, and then moving on to exotics for the next couple. So hopefully it's not going to be too dense. You're going to enjoy it. If not, please don't tell me. And then we will have a nice chat. So we'll see me walking around for each other on this. So today we're going to focus on the strong interactions. Not a very cool plot, but I think it's one of the things very well that we want to look at. And we will say a few words about the electromagnetic and electric interactions just because we need them to basically determine things that we're going to measure in the experiment. So let's say, because I'm going to do a brief motivation, that you don't really care much about the strong interactions, but you care about bigger questions and you don't want to look at light particles, but other things. Well, they play a key role at early stages of our universe. So, we want to understand synthesis or biogenesis. We're going to need to understand them. It also explains us how the cores of stars are stable and how the elements are produced either in stable fusion or supernovas. And also, if you don't care about any of this, you just want to look for standard physics for the beyond, they basically give us the tools that we need in hydrophysics to look for other kind of hidden interactions that we don't know about. So today we're going to be talking about bound, not exactly bound nucleons, but bound hadrons, where the mediator of the force is the gluons. If we were to put a picture, to try to make a pictorial representation of QCD, we would have a quark and an anti-quark, and in between lots of gluons. So if we were to simulate it or just draw it with an ordinary flux tube model, it would look something dense like this, which means that gluons aggregate between quarks, and the force is constant with the distance. But it also means that the potential grows linearly with the distance. So in order to split 2 quarks apart, we need an infinite amount of energy. The scales involved here, femtometers, are roughly speaking 50,000 times smaller than an atom. So we are very small scales, right? This doesn't happen when 2 particles, like 2 mesons, are split apart. And my very best friend is the pion, which is not as known as the proton for these reasons, but we will play with them because they appear in final states and they populate our final states in experiments. In particular, you're going to have lots of lectures talking about this in detail and digging deep into the internal structure of these guys. For us, this is just going to be the simplistic picture of a balanced quark and an anti-quark with a 1 gluon, no more than that. Okay? So we're going to be talking about the quarks, There are 6 in here. We're gonna forget about the top one because I don't like it. And then the glue. And it's all we care about in the stars. So pretty much like you could do on a lab, where you get your source of light, and then somebody asks you, what is it made of? So you are gonna split the colors apart, you're gonna use some prisms, some diffraction techniques, and then some detector. And at the end of the day, you're gonna give me the light spectrum. These are some peaks depending on the colors that the light has. So you can tell me, it has a peak to green or to blue, and it's made more of this or that. Now you can do this in quantum mechanics, the hydrogen atom gas, and this is basically going to tell you which are the lines of emission of this atom or absorption, depending on what you're looking for, right? So probably most of you know about this, and most of you have also played with this. So we're going to try to relate that to what we do in QCD. So first things first, if you were to do that with a hydrogen atom gas, and then you compare to what we know about quantum mechanics. Let's say we start by the simplistic Schrodinger non-relativistic equation, and then you get the energy levels. So you have quantized your atom, you know that the levels are quantized, and then an electron basically can absorb photons and get excited, or emit photons when an excited electron drops from one level to the other. And so in doing so, you can test this equation here. Not only can you test it, but if you had utmost precision at determining these levels, then you could also check for possible corrections. Now, we only know quantum mechanics. Let's assume we know nothing about QFT. These corrections are going to motivate the introduction of something beyond what we know about quantum mechanics, right? So if we want to get them right, we start by measuring something and then testing if what we are developing is correct or not. Okay, we're going to try to do something relatively similar for QCD. This is the Lagrangian formulation of QCD. It's just a one-liner. That's fine, seems easy, right? There is only 6 building blocks, remember 5 because I don't like the top, and then the glue. Problem is, we cannot extract information directly from this Lagrangian at the hadronic scale. Interactions between these two guys are too complicated for us to give you a closed formula for how this looks in the hadronic scale. Let's compare it to QED first. So for QED, once again, we have a one-liner Lagrangian. It doesn't look very different from QCD, does it? Now, the first thing that is interesting for us is that we can calculate perturbative expansions in QED based on the assumption, based on the fact that this parameter is small. So if I was to use a perturbative series and I get different terms, right? This one should be much smaller than the first one. This one should be much smaller than the second one. As at some point, I just can neglect these terms, stay with it, or stick to the first ones. And I have a decent quantitative description. We cannot do that in QCD, as we will see. The second thing is photons do not have charge. So they don't see each other. They only interact with charge. So they interact, for example, between electrons and protons, but they don't see each other. And this means that our theory is abelian, or the classical limit is going to be linear. This is going to recover into linear Maxwell equations. Now, this is not the case for QCD. First things first, gluons, the mediators of force, see color charge, which is basically the characteristic charge of quarks in thermodynamics. But they also carry these color charges. So gluons not only interact with quarks on these vertices, they also interact with each other. So wherever you have one gluon, you can have 400 or 1,000. And it's a matter of seeing if this perturbative series, if this perturbative expansion converges or not. Because if it converges, well, still you have tons of gluons, but you can do something. If it does not, then one gluon, 1,000 gluons, and 1,000,000 gluons are identically the same. Okay, so this is this beautiful plot that gives us an idea of the alpha strong parameters, so the equivalent of the coupling in QED that we use for the perturbative series. In this case, it's the strong one. Now, we see that it's running lower and lower when we increase the energy. So if we go to the Large Hadron Collider, CERN, this scales is alpha is 0.1. It's a small, it's fine. We have a Large Hadron Collider and then we have very energetic beams, then this thing can be perturbative. And then you are going to have lots of different ways of explaining jets and perturbative series and small x and everything. And because you have lectures that are much better than I am at this, I'm not going to say anything here. You will have lots of lectures here. I'm going to be here. So I'm sitting on top of a proton and a neutron, where the energies involved are of the order of 1 GeV. Remember that the mass of the proton and neutron is of the order of 1 GeV. And the problem is alpha strong is running high, right? Very fast, very quick. So it's going to reach a point where we cannot calculate perturbative expansions. This makes no sense. One gluon and a million gluons are one and the same. So we can't forget about that. We cannot go that way. Instead of having ordinary quarks and antiquarks, our blocks are going to be hadrons. We cannot split them apart, and wherever they have color, they interact through gluons, which binds them together. So what we find in nature is color singlet objects, these hadrons. So this process where we go from a one-liner Lagrangian to our hadrons, this hadronization, is a bit complicated to explain, and we don't really have an answer for that. I would like to understand the connection and see if we can gather information of the QCD by doing spectroscopy. So pretty much that we are going to relate the hydrogen spectrum, the hydrogen atom spectrum of the lines, with understanding the description of this Hamiltonian possible corrections. We would like to relate the book and QCD. Now, this bar is killing the website link, but this is the particle data group website. Most of you probably know about it. If you don't, just ask me for the website. Just have to text PDG or Google and you will find it. But the idea is that this book, on top of many other things, thank you, Martin. It's going away.
You can click on chat, and close chat, and everything is up.
Okay. So this is the website. Thank you very much.
Okay.
And so inside this book, we will have tons of different particles collected and classified by quantum numbers and properties. This is a table of Mesons. And you know, there are a few hundreds here. There are many more actually. These are the ones that are decently determined. Okay, its masses and properties. No, we know it. So there is like a collection of quantum numbers in here that we will talk about in this and the next lecture. And there is a collection of masses. So what I want to say is that pretty much like a hydrogen atom produces levels because they are quantized. And this is the spectrum of the hydrogen atom. QCD produces levels. And this is the spectrum of QCD. All of this, each one of these, are created by a bunch of quarks and gluons together. And all of them arise from the same, basically the same 5 quarks that we were talking about, and the same Lagrangian. But they are very different. So the idea is, how do we relate one with the other? Can we tackle them now? Or can we classify them? Can we learn something from them? So these are, so yeah, anything about it? Yeah.
That's
And this is not just me and my charlatanry. So this is included within the long-range plan of our beloved Department of Energy, which states basically that hadron spectroscopy should illuminate the QCD interactions that binds the quarks. So the idea is that establish a connection between this, forget about the top, and then this, which is what we measure in experiments. And here is where we stand at. It's slow, it's complicated, but hopefully. So let's say that you never care about hydrophysics. You don't care about the spectroscopy, you don't like experiments. They're complicated and expensive. And you just want to look for the beyond because we already have the Lagrangian of QCD. So you want to build another Lagrangian. One of QCD is already done. So you go and join an experimental theoretical collaboration that's going to work on beyond standard model searches. And let's go to hot topics. First hot topic, the anomalous magnetic moment of the muon. These determinations in red are theoretical predictions. The blue band is the experimental measurement. And there is a big tension, right? It's 4.2 signals nowadays. Could be about 5 in the future, we don't know. The idea is that in order to determine this with precision, you're gonna describe the rho and omega line shapes. And these are 2 of the states that were on that list in the DDG. So you better know about hadron physics and spectroscopy if you want to look for this hot topic. Okay, you don't care about that one. What about probability case? Where there are observables that are in tension with the standard model physics, it should be zero, but it's around here, so it's several seconds away. Well, also, if you want to learn anything about them, you better know about some hadron physics. What happens if you join an experiment that wants to detect dark matter? You are gonna play with protons and neutrons, with neutrons at the end of the day. So you better know something about the pyronucleon sigma. We have an expert in the audience, over there, that has calculated it a couple of times, Jose. And he will tell you that you need to know about hadron physics if you want to tackle that baby down. So no matter what, if you care about hadron physics initially, or you want to look for the beyond, you better know about these things about the spectroscopy. Okay, so in the rest of this first talk, this is going to be a very simple introduction to the foundations. So very simple properties and the features of interactions. So I'm going to start with rules of thumb. Basically, this is true, but I'm not going to prove any of them. The first one, the angular momentum, and I will use J or discrete L, depending on where we are at, is conserved. You only have to invoke that the theory is invariant under rotations, and then you recover this. So every particle that we care about has a well-defined angular momentum. It's a very good quantum number. Now, when allowed, strong interactions dominate electromagnetic ones. So we will dominate photons and these dominate double bosons. Okay? When allowed, because strong interactions carry more restrictions than the others. So sometimes might happen, something cannot happen here, but can happen here, for example. Now, mesons, in general, ordinary ones, are made of quark and antiquarks. But in general, I would say even number of quarks and antiquarks. Baryons are made of 3 quarks in the ordinary picture, but we can also have pentaquarks or heptaquarks. So an odd number of quarks. And as I said before, we will forget all the baryons in these talks, okay? So first things first, standard model interactions, all of them preserve the baryon number, and this is 0 for us. So that was quick. We are not going to look into baryons, so this is 0. Second and third, QD and QCD preserve flavor, defines the rest between the number of quarks and antiquarks, and they also preserve baryon. For example, a pi0 has no flavor. If you remember the quark model description of a pi0, but in the balance picture, this will be basically up anti-up minus an anti-down. We looked into that. So it has no flavor. It can decay electromagnetically. And this carries consequences for us in detectors. Now, electron interactions, double bosons, do not preserve this. So basically, a pi plus can decay for a double plus. And this carries also consequences. Now, if we are going to look into the case, we will preserve in every vertex momentums and the energies. And this is going to be particularly interesting for us. We will play with this in the lectures on Friday. So if we have a 2-to-2 process, because most of the stuff we measure and that we understand is scattering processes. So 2 particles collide with each other and then produce another 2 particles, or 2 particles produce themselves in the final state. Then we can define what are called demandless variables. Can someone tell me why did I say these are, these are invariants. And they are defined this way. So can someone tell me why are these invariants? Why would I use these 3 variables instead of the momentum? They don't depend on the reference frame, so they are very useful for us. Now, the 3 of them, let's say that we don't need the 3 of them. With 2 is enough, because they respect this relationship. And this I leave as an exercise. You don't even need the explicit formula of the momentums to recover this expression. But yeah, these S and T variables that are going to be the ones that we use to define our amplitudes are very relevant for us, you will see. So another rule of thumb, apart from claiming that QCD showcases many unique features, and we'll see in a second, another rule of thumb is that the more phase space is open, the greater the decay. And we're going to do an example of this. So if we have a phi meson has 1,020 MeV of mass. It can decay either to 3 pions or to 2 kms. Sorry, this is kk bar, 2 kms. So which is the mass of the 3 pions together? 520. Which one is the mass of the 2 kms together? It's almost 1,000. So can someone tell me, by this rule of thumb, which of the two decays will be greater? The jumping mass from here to here is much greater than from here to here.
When you say that the decay is greater, you mean it has a larger cross section?
Indeed. So which one of the two would you think, based on this rule of thumb, would be greater?
I would say the pion triplet.
Yeah, but that's incorrect, because this was a trap. Yeah, sorry about that. But thanks very much. I needed someone to. So the idea is, and this exemplifies the kinds of diagrams that we want in the strain interactions. That decay, and it's true. This is, for example, an idea of learning about the phi meson. The phi meson is built upon a strange and an anti-strange quartz. Okay? Pions are only light quartz. So when we connect a phi going to 3 pions, we can have connected quark lines, right? So one is a strange anti-strange, the others are just light. And QCD prevents us from having quartz changing flavor. So it must be connected through gluons. This is the picture. Now, a phi meson, because it's a strange anti-strange, can be connected to KK bar through quark lines. This is how, for example, we learn about the phi meson. Now, if we can get a Feynman diagram, or a diagram, even if it's not a Feynman diagram, something that represents the reaction, we can cut vertically just gluons, then this is suppressed, heavily suppressed. And this is the OCI rule. This way, one would expect as a rule of thumb that this would be greater than this, but it's not experimentally. And the way of explaining this is this OCI rule, which also tells us that the phi is indeed a strange anti-strange. Because if it wasn't, then it would decay mostly to 3 pions instead of 2 Ks. Now, this is even more suppressed for heavy mesons. Can someone tell me why this is even more suppressed, this OCI rule, for heavy mesons? Well, the answer is here. This alpha strong runs slower with the greater the energy. So if you have a psi that has almost 4 GeV of mass, and it decays to 3 pions, then the phase space is much greater. The difference in energy is much greater, right? So basically, this alpha strong is lower. So it means that it's even more suppressed because each one of these photons interacts more weakly than before. So is there any question to this point? I'm gonna put some question slides from time to time so I can drink some soda.
So you said the phase space has got something to do with the mass difference?
Right. So the idea is that in order for this to decay to this, right, because energy must be preserved, this mass has to be greater than these objects. If it wasn't, then it couldn't decay. Now, the difference between this mass and this mass is giving you the energy that this carries when it decays to these objects, or basically the free energy that these objects carry when this thing has decayed, right? That is the phase space. So the bigger this difference, the more energetic these three will be when they show up out of the decay. And as a rule of thumb, when that increases, then the decay is greater. Depending also on the quantum numbers, and we will speak about that in next lectures, the shape of this phase space increase will be different, depending on the angular momentum in particular. But as a rule of thumb, the phase space will increase because the phase space depends on the momentum of these guys.
Right, so as the phase space increases, that decay channel gets suppressed more.
No, as a phase space increases, decay channels increase as a rule of thumb. Because if you look at the formula of the cross section, it depends on the phase space. The phase space will be in the numerator in that sense. So if one increases, the other increases. This one is suppressed, right? Because it only has gluons mediating it.
But this one has more phase space to cover, right?
Yes, indeed. But let's say the couplings in these vertices make it much smaller. So it has, so as a rule of thumb, because this is why it was a trap. As a rule of thumb, this would be greater because it has much more phase space. But the couplings here, because they are only gluons, is much lower than this connection. What I wanted to, apart from the fact that QCD is very complicated, I wanted to stress the point that for strong decays, we look for this kind of diagrams, not this kind of diagrams. So we want continuous quark lines. Basically, what we don't want is diagrams where we can cut only gluons vertically. So yes, this could be greater the phase space, but still it's suppressed because you only have gluons.
So I understand that the only gluon lines are suppressed, but why?
But why?
Yeah.
Well, for example, you can look at this. So you have, let's put an example with that psi. This is almost 4 GB. This is 3.77. And this is 500. The difference is 3 GB, right? If we look at the alpha strong up in here, and the 3 GB scale, you probably don't see the x-axis, but is here. So alpha strong is 0.2, which means that this value is low. Whereas these other decays, work lines, are not addressed by any means. So in comparison, one versus the other, this one is great. And if you have like 100 GB difference of mass, of course this alpha strong is even slower. So that is why it separates. This is a bit of hand waving, but gives you an idea. Is there any other question?
Why are we ignoring the top part?
Because it's super heavy. And so it means that hadronizes many things, and I don't know how to explain it. So it doesn't create resonances, maybe. It doesn't, in principle, create resonance because it's so heavy that it hadronizes many other products that have so much energy that ends up in a different, let's say, energy scale where you have other effective field theories and ways of describing things. So it's not exactly like lower mass hadron physics. So if you have a top that's 170 GB, then this thing will indicate the products carry so much energy, right? That you are no longer in this region. You are again in this region, right? Because it was so heavy when it came to lighter products. Then most of the energy is just free energy that goes in the momentum. And so it means that it's no longer honest to God hadron physics. It's something that perhaps will be perturbed. Yeah.
So I just wanted to follow up on the questions the students asked. Do I understand correctly that the suppression factor you're talking about is just by powers of alpha S? So
The you is yes.
the suppression margin, is it just by powers of alpha S?
5 powers, is it?
No, is it by powers of alpha?
Oh, well, I mean, this is hand wavy, so I don't think it's exactly that way, but it was my way of explaining it. So in principle, if this is, the difference is very energetic, then I think it could look like that. But in this case, I don't think it's just that.
Right.
So this is just very hand wavy.
So there's no parameter that explains why.
I cannot
suppressed on the
calculate,
left side.
right, I cannot calculate algebraically this. This is a hand wavy way of describing the fact that we can have this kind of diagrams. And I can do an explanation for heavy objects that makes more sense. But for this, it's just hand wavy.
One follow-up question to that.
Yep.
In addition to the number of strong vertices, we're also looking at the mass of the bound system to get an idea of how strong that coupling is.
Okay, can you repeat again because I didn't get.
I'm thinking one, in addition to the number of interaction vertices, is it true that another reason why the D decay is greater than the pi decay, in addition because something about the ground state of the D mesons leads to a lower coupling due to a higher Q squared in the ground state?
You mean, so here we are talking about the psi, right? So this, and then you are saying that because of the D meson properties, I don't think I'm getting the full
I'm
question.
trying to understand the relationship to the graph above, where
Oh,
as
right.
you go to
No,
higher Q
because in
squared,
this case, because of the quark content of the psi, you could draw continuous quark lines to the 2 dimensions, but you couldn't do it to 3 pipes again. So it would be a similar kind of diagram. So I didn't draw the diagram because I was lazy. But you could have continuous lines to the D plus D minus from a psi, but you couldn't have it for example, 3 neutron piles. It would be more or less like this. And so what I was saying is here it would be even more suppressed because the difference is large. So that is the whole argument.
thank you. Let me try to refine my questions
Yep.
then. Is there a contribution to the difference in the decays due to the difference in coupling strength, given the energy transfer Q squared that's required for these two?
Well, yes, of course. I mean, it depends. I mean, the thing is you cannot calculate them depending on the particle. This is heavy, and so you might get some models that describe and write the formula. But as a rule of thumb, this decays and the strength of them will depend on powers of the momentas of the particles at the end of them, which depends on the angular momentums of these objects. It's a basic requirement. So we would go for the 3 piles. And then it would depend on something that what could be a QCD give an amplitude that I don't know about, that you can, in this case, for example, plug in a model, and then you could calculate them and get these coupling factors, which I don't know exactly what the numbers are. The idea is that as a rule of thumb, it depends on the phase space times powers of the momentum. And I'm trying to just make you realize that this is not always the case. It's just a rule of thumb.
So when you have heavier masses decay,
Yeah.
if the decay products have the same quark content, they are favored more irrespective of the phase space dominance.
Okay. Can you repeat the question?
So basically, if the decay products have
Yes.
the same quark content, then they are favored more.
Well, I mean, by saying quark content.
Like in the case of phi.
So the thing is, so the thing with the quark content is that flavor is always percent.
Right.
So that is like, the idea what you mean by quark content is this, right?
Yeah.
It's a continuum set of lights. So for example, here you have an S quark and an anti-S that can go continuously into the chaos. Yes, this is predominant.
It's the same case over here as well.
Exactly. So this is the case. You could draw something like this for the D plus and minus. You couldn't do it for the 3 pi. And this basically tells you that we care about the diagrams on top, not the ones in top. When the two of them are allowed. Sometimes this one might not exist, but this one might exist. We will see an example of something. Okay. So I'm gonna continue. I still have some slides. But the idea is we started from 5 quarks and 5 anti-quarks. And here I am introducing you a table of mesons that are almost all stable under Qcd interactions, and they are 28. So what happened? We went from 5 degrees of freedom to 20. I'm saying these are the basic building blocks for us. This doesn't look good, right? I mean, you don't get a 1 parameter formula and then give me 10 different parameters at the end of the day. This gives me 1. So this basically exemplifies how complicated Qcd is in the hadronic scale. And we are going to take a look at the ones that we care about the most in experiments in order to do a spectrum. So let's start with the pylons one first. So they are made, and we will play with this in the next lecture, by an up and an anti-down quark if you are talking about the pi class. It can be an up and an anti-up if it's a pi 0, combinations of up anti-up and the anti-down. The idea with the pi class, as I said before, is that it decays through W boson. And this is the weakest of the 3 interactions. So it lives for a quote-unquote long time. The time, the travel distance that it reaches to the first frame is relatively long. What does it mean? It's charged, so for example, we can accelerate it on a beam, and it lives for a long time. So we don't lose them when we accelerate them on beams, right? So you might want to have them on initial states of the detector. It could work, you are going to lose them, but it still could work. What will happen with a pi 0? A pi 0, as I said before, decays electromagnetically, and this dominates electron-wave reactions, so the time, the lifetime is way smaller, which means that in its first frame it lives for like 26 nanometers at the speed of light. This is not good, right? Can you build a huge detector and do everything within 26 nanometers, or a bit more than that? But I cannot. The idea in here also is that it's neutral. So it will be very complicated for us to accelerate them because they don't have any charge. But these are very good for final states, for example. Can anybody tell me why are they good for final states? When you have a reaction and they show up in the final state. Why? I mean, it's neutral. Why don't we just say this is terrible because it has a half charge? Because it splits into photons very quick, and then we can get these photons inside our detector. So pi 0 is fantastic in final states. Okay, let's move on. And on to the chaos. K classes or K minuses is basically identical. The idea is that they all decay through electron-wave reactions. So we always have a W, in this case plus, or minus for a K minus, and then a CK matrix element. So the idea is that they live for a long time. Roughly speaking, the time of travel is 4 meters. So again, we can do something with them. We can accelerate them. And they live enough so we can play with them in the initial states of our accelerators. The neutrons are more complicated. So we have 2 Ks, the K0 and the anti-K0, K0R. And first thing is that they mix with each other. They mix with each other because they are not agent states of the Hamiltonian, okay? Instead, we define our agent states to be these two guys, K0S and K0L. These guys don't mix with each other. And they are called basically K0S because it's short-lived, K0L because it's long-lived. We are that smart. So one has around 3 centimeters of travel distance, and the other one has around 15 meters. But there's a huge difference, right? So can anybody tell me which one do we want for the initial states in our detector? Anyway.
K-long.
K-long. We want the K. Now, do we want any of these two in the final states of our detector? Indeed. So the K sort also decays pretty much like I0 into products that we can measure. So that's fine with the final state. But the K long is not charged and it's very long. So it's cool on the initial states, but on the final states, it would fly past through the detector. So we won't see anything, right? So we don't want these guys in the final states. We want this guys. We want this in the initial states. Now, the masses are different, and we are going to see a cool phenomenon. And this means that a K0 and a K0 bar are going to oscillate between one and the other because they are made of K-longs and K-shorts. In principle, if we see the temporal evolution of a K0 state, let's say that I get a K0, I let it evolve over time with the Hamiltonian, and then at some point calculate the probability that this K0 is still there, then we will have this formula. And what I can care about most is the mixing there, because the masses are different. Now, I don't have a cool plot about the mixing of neutral kaons, but I do have one for the P measures. And then, no, they are not called values, okay? The idea is that pretty much happens for V0 and V0 bar. And this was measured by LCD. And you can see with which precision it is measured. So this does happen indeed. And we can see that all these things work, right? Make sense. So now we have the full list of 28 mesons. And the problem is, this is just the beginning. I didn't even start talking about barriers. And these are just, let's say, the stable ones. So what is going to happen when we start adding barriers and they're stable and everything? We're going to have thousands of them. So we're going to start packing them in, well, basically in groups by using symmetries, right? Symmetries are good, and Qcd has lots of those. So I wonder if, you probably have seen this already today or just today. Yes, you have seen it. I just got the double check. So first things first, if we get the QCD Lagrangian, and we focus only about the direct part of the Lagrangian, we will see that it depends on the mass of the quark. It doesn't depend on anything else, right? So in principle, if the masses of the up and down quarks, let's say, that are the same, then one would expect this Lagrangian to be invariant under rotations between one and the other, mixings between them, right? Well, it turns out that the masses of the two quarks are much smaller than the ones of the hadrons. So this is a very good symmetry. And this is called the isostate. Because we have a two-level state, right? We have one HUGS system, and it has an up component and a down component. Once again, we are very original with names. And so we can define the isospin numbers. And it's going to be a very good quantum number for us. In particular, we are going to use the third component of the isospin a couple of times. Remember, binary number is 0 for us. And most of the time, examples of them going to put the spin is also 0. So the third component of the isospin of a meson, in most cases, my examples will be just the charge of a given meson. So with this, we have up and up and down and down. And we could in principle mix 4 different mesons with them, right? We're going to recover with that 3 pions and some, and I'm not going to go into that sum. Okay, let's make everything slightly more approximated. So let's say that the strange quark mass is also much smaller than hadrons, which is true. At the same time, it's much bigger than the mass of the light quarks. So this symmetry is just going to be approximate. Now, if we have 3 different flavors, and a meson is made of a quark and an antiquark, how many mesons can we build with this? 3 times 3, right? So in principle 9. which could be described as 8 plus 1. And I forgot to put the figure. So here I'm showing you 8 of it, which is the octet. And then I am not showing you the nonce just because I took this picture from Wikipedia. And this also happens for baryons. In the case of baryons, how many would we have in a multiplet? In principle, we have 3 quarks per baryon, and each one of these can have 3 flavors. So it's 27 of them. And then we put the strip as different symmetry groups, right? The idea is that because this is an approximated symmetry, but because it's decently approximated, then the masses, compositeness, and sizes of this object, one would expect that naively speaking, they are related. Okay? So let's take a look at how we build them. And let's do an exercise. I said before what the baryon is made of in terms of quarks. Let's take a look at it. So what is the charge of a pi zero? Anybody? 0. What is the baryon number of a pi zero? And the spin? 0. So the third component of an isospin is 0. And this is the table of Cleve's coordinates, and now this thing is in the middle. But I promise you there is a 1, 0, and 0, 0. Let me see, I can do this myself. So if I click on it, am I gonna break something?
No. Just
Click on the X.
on the X.
Okay,
That's why.
fine.
Might need to click one more time to make sure you can use the.
Yes, good idea. Oh no, I could. Yeah, you saw the solution. Okay. So we see here for the Cleve's coordinate table that probably most of you played with. So we have a 1, 0, and a 0, 0. The lower column is the lower row is the third component of the isospin, which we already determined here. What about the total isospin? What is the total isospin of a pi? Is it 1 or is it 0? 1. There are 3 pions, so it has to be. Okay, so this is the state of a pion made of quarks. So we are going to have the terms, and because we have to use square roots wherever we see these numbers, is 1 over the square root of 2 up anti-up plus 1 over the square root of 2 down anti-down. So the solution is, wait, it's a minus there. Why is there a minus there? Because I defined the anti-down this way. So there's a minus there filtering there. Okay, so we know more or less how to build our basic blocks, or at least how to take a look at the word picture of these basic blocks. We will take a deeper look into the quantum numbers in the next lecture. So in order to finish this lecture, we're going to go slightly into something that I find very interesting, but it's kind of going to be useless after I introduce it, because we are never going to mention it again. But it gives an idea of the masses of these quarks, of these Mesons, sorry. So as I said before, because the masses of these 2 quarks are very close to 0, the Lagrangian, if they are 0, identical to 0, then the Lagrangian is invariant under chiral rotations. And this is called the chiral symmetry. Now, I also checked that you have already seen conserved currents and then other theorem. So this means that we're going to have some conserved currents associated to the fact that the Lagrangian is invariant under a given rotational symmetry. So in principle, we're going to take a look at this, at the action. Okay. So the problem is, okay, Lagrangian is invariant, but our ground state is not. Our ground state is not made of a quark or an antiquark. Our ground state is made of hadrons. So the Lagrangian is invariant, but the ground state is not invariant under the same symmetry. And so it means that this symmetry was spontaneously broken. You probably have seen the picture of the Mexican hard potential, and I know it's used everywhere, but they have another way of explaining it. The idea is that the ground state went from metastable to something stable that doesn't respect the same symmetries that it had before. But the Lagrangian is invariant under this symmetry, which means that these charges are conserved and they commutate with the Hamiltonian of Qcd, because it commutates this relation is 0. And acting on the vacuum, of course, is 0. My construction is just this. This part is Hamiltonian acting on the ground state, so that is identical to 0. So we end up with this term, which is basically the Hamiltonian acting on the charge is conserved on the ground state. So there can be two things. Either this Q annihilates the vacuum, as it means that the ground state is also invariant under this symmetry, or it doesn't, which means that it's not invariant under that symmetry, but the Lagrangian still is. So if it doesn't, then it will produce something. It will produce something with these quantum numbers. And these quantum numbers are basically angular momentum 0, a negative particle. So it's what we call a pseudoscalar. But then, if it doesn't, because this relation is still true, the Hamiltonian must annihilate these particles, which means they are massless, right? They are agent states with mass 0. So we basically got a set of particles that have these quantum numbers, pseudoscalars, which mass should be 0. And there are these guys. Now, to tell me, no, the pions have mass. You're wrong. This is true because the symmetry is also explicitly broken. The masses of the quarks are not 0. So the chiral symmetry in the Lagrangian is only approximate. It means the greater the mass of these quarks, the more broken the symmetry is. And so the more mass these objects will acquire. If the masses of those quarks will be 0, then the masses of these guys, of the pion, kaon, and eta, will be 0. So now, why do we have this difference in mass? So the pion is very light, okay, it's roughly speaking 6 times, 7 times lighter than a nucleon. But why is this guy much heavier than a pion? I just made an argument and I call them all, you know, these pseudo-constant bosons that are called. But why is this 3 times the pion? Why is this also 3 times the pion? The answer is because this one only contains light quarks, which break the symmetry. It's a very little breaking of the symmetry. But these two guys have a strange quarks inside, which have a much bigger, much greater breaking. And so there is a relation between the explicitly broken symmetry and the masses that they acquire. Now, it's also interesting to see that even if it's for different reasons, this hierarchy stays in all these kind of multiplets. So I introduce you to the multiplet that we'll discuss in the next lecture, which is the vector measure. And the idea is that if we look at particles in this multiplet, these 4 here, that only have light quarks, I promise you, they only have light quarks, then their masses are very similar, right? But now if I look at something like the K star, this guy has greater mass because it has 1 strange quark. And if I look at the phi, which has 2 strange quarks, then it's even greater. It's an approximative theory, and the idea of classifying them doesn't give you the exact same answer because there is a 200 or something the difference in mass. This is only 1/4 of the total mass of the system. So it's a decent approximation, right? And so I'm going to stop here, and we'll go into details about this vector measure multiplet in the next lecture.
Well, thank you very much for this amazing lecture. Arkaitz, questions from the audience?
Yep.
So you talked about the Mexican hat potential, right?
Yep.
So for the excited states, it preserves chirality.
Yes.
Yes. Now on the ground state, the chirality is broken, which means this Mexican hat essentially tilts to a different equilibrium point.
Yes. Maybe, yes. Well, yeah. I mean, so this also was taken from picture reviews and a description of the linear sigma term model where you only have these states as the constituents. So that's also what you see full symmetrical order.
My point being, when it becomes the ground state, the Mexican hat actually tilts.
It has to. So the idea is that this Mexican hat, if I don't get it wrong, you will have some moment. It's never going to be exactly like this. First things first, all these modes have acquired mass. So the ground state won't be exactly like this. This rotation is not going to be like this. It's going to be full symmetrical. Otherwise, they would all have the same mass, and they don't. So, and then also the modes that acquire mass here, they don't have the same mass. So there is also a difference between that. So it must not be exactly that symmetrical. This is another simplification. Because I mean, if it was like this, then these pion modes, let's say that I put the whole multiplet in here, then all of them would have the same mass, and they do not. So there must be a difference between them. More questions?
More questions? In the back?
Yep.
Can we compute the mass of the meson by only using the quark mass? There is a formula or?
Yeah, so for the people online, so they are asking if we can compute the mass of the meson by just using the masses of the quarks, if there is a formula, and there is. This is an effective field theory. So you will describe it with a pinch of salt, but it converts decently well, I think, for the mass of the quarks. The idea is that you are going to have a parameter that relates basically the masses of the quarks, the quark condensate, to the masses of the supercostal bosons, and you will recover a parameter that at tree level can be related to, for example, the decay constant of the pion, and then a higher order it must be fitted to data. Okay? And also, yeah, that's right. So another interesting thing that I didn't say is that the masses of these guys depend on the masses of the quarks. So for example, how would you expect the mass of an ordinary meson to depend on the mass of the quarks? We have a quark and an anti-quark. Do you expect it twice the mass of a quark? Do you expect it Q squared? Yeah, but if you were to relate the two equations, let's say we have a phenomenological formula that relates the two. So would you expect it to be linear? Would you expect it to be quadratic? Linear. So linear is what happens for these guys, but in some point model calculations, you can see that for others it's quadratic. So these are slightly different than others.
What would be the reason why K longs and K shorts have different masses?
Oh, I mean, in principle, they can have different masses. The quarks, the light quarks that are inside are not exactly. K longs and K shorts are made of K zeros and K zero bars, right?
Right.
So it's not a simple of a picture, but let's say that we have a K zero and a K zero bar, or K zero. Let me go here. So then we have it here. Well, so the idea is that you have different mixing between these guys. And so in principle, if I'm not mistaken, no, I mean, they have the same light quark. So I really, no, the argument that I was about to make doesn't make much sense. So they are allowed, and the argument that the simplistic argument that I was about to make doesn't make much sense. So I'm just going to stop here.
I can know the argument.
Yep.
The mass difference is incredibly small.
Yes.
Due to the weak interaction.
Okay, that's a good point.
And it is actually higher order in the weak interaction. So it goes like G squared. So for that reason, it's an incredibly small.
That's right.
Is that like experimentally measurable, or is that just like?
Yes. You
Okay.
can
The method to measure it is that you have a K long beam, and then it goes to a material, and the interaction with the material, even if it's rather weak, allows to regenerate the K short. Okay, so yes, they say the weak interaction between the K long and okay, makes that the eigenstate is no longer the K long, but now it's a mixture.
So it's something related to this
There's
formula.
a way to extract from that cross section.
So is it something related to the formula that gives you the temporal evolution of a K0?
And yeah.
I mean, in principle, you could.
The width of the lifetimes are a little bit different.
Oh, the lifetimes are different.
Because the K short, the case is 2 pi, actually the K long, the case is 3 pi. So this calculation of that whole race is actually one of the problems that people will look at Lattice Qcd.
So it is that the K short and K long are city agent states, right? So that's why they decay to different things. And the strong interactions, you cannot mix them because the strong interactions per se is CP.
It's just interesting because you said that like K shorts decay to 2 ions and K longs decay to 3.
Yeah,
So then in the argument earlier, when you were talking about like the amount of phase space dictates the rate of the decay, why then would K longs take longer?
oh,
to decay?
CP. Probably is just because of the CP numbers that
Okay.
each one of these has.
We have a question here.
Oh, yeah.
Go ahead.
So when you're showing that like diagram that had like all of the different mesons on it, like the different combinations. where
The
you-
table, you mean?
Or no, this was further on towards the end.
Okay. You tell me.
Yeah, that one.
Yep.
So this isospin only holds like, assuming we're working at high energies where you can kind of treat, or does this only hold at like high energies where like up, down, and strange are kind of considered like the same like mass eigenstates
Okay.
of quark? Because
So I see your point.
what I was gonna ask is, is there another way to like formulate this where you could include like charm or bottom, like if you were at like high enough energies, or are those just too massive?
I mean,
to
you can
really-
approximate that. So the thing is, when we are looking at hydrophysics, right? By definition, the scale is 1 GeV,
Mhm.
because otherwise you cannot produce hadrons, roughly speaking, right?
Mhm.
All of them have that mass. So 1 GeV is already much greater than these two masses. Because these are like a few MeV on the MS scheme, you know, the MS bar scheme. So the idea is that because it's already much greater, when we play with hadrons, this is already effectively respect. If you were to include, let's say, a charm, then the scales you would have to go to so that this symmetry makes any sense. And that's the idea. It's a scale where you no longer have hadron physics, you have a perturbative QCD description. So the objects that you have there is not a different table with much more massive objects. You would have some perturbation theory.
And then building off of his question, building off of his question, what if you didn't impose that you were just trying to rotate one particle into the other, but you didn't leave, say, the length of the vector constant either? So it's like rotating and stretching to, are there any attempts at doing that to account for?
Well, the idea is that, yeah, so I get this right. So what is it? I mean, it is invariant under these rotations, right? So what you are describing, when you have this space where you have all unit vectors, because you are describing the rotation between two bases, between two elements of base, is not something that could give you. So to say, it's not anything that will give you a different kind of particle system. So it's only variant for that rotations. And it only makes sense that you do rotations over that system.
But there's no, you can't widen the class of transformations to allow for not just the rotation, but changing.
Because when you change in the distance, what is that kind of distance that you have in mind? It's not the distance between quarks. It's not the distance between the system. That is what I'm saying. So for example, let's say that you don't have a unit vector, right? So instead of like having an up quark, then 1.3 up quarks, this is what I'm asking.
Oh, okay.
So this is what you end up with. You don't have unit rotations.
In my,
And this is not a physical system. It's not something that gives you, let's say, a unit that you can really do any observable or anything, right?
okay, thank you.
At the end of the day, most probably because of how the Lagrangian is built, those things just don't make any sense. It must be invariant on the unitary operations, but the rest of the operations that are not unitary don't make sense in the Lagrangian. And so this unitary means that it's a unit vector. And you can see that also in the effective theories. In this sense, I mean, unitary mean, for example, it's well, I have it for the next lecture, but this kind of is rotations.
Before continuing here with questions in the room, I would like to know if there are questions from the remote audience. Please feel free also to comment questions or raise your hand. And we continue in the room. We can get some more questions. Matt, have your raised hand.
Oh, yeah.
Yeah, I was gonna ask this maybe offline, but I guess if we've got a moment now, can you remind me please why the D bar is defined with a minus sign, but U bar is not? This resulted in the ISO triplet changing sign to look more like an ISO singlet sign.
Yes, well, I think at this point, so to be honest, I always play with this being a positive sign, but I didn't pay much attention. I mean, when I was using this, I was using a textbook. That's why I decided to go with the nomenclature. But yeah, so this is also why I reminded it, because there's a minus sign because this is defined that way.
Okay.
Always very trouble. Yeah.
Well, if we don't have more questions, maybe it's a good time for the break.
Yep.
Well,
Just one announcement. There seems to be, there was a little bit of confusion about the channels on Slack. We always mention channels here, channels there on Slack. All the channels are public, but doesn't mean that they are upfront in your Slack list of stuff of channels you are subscribed to. So you have to subscribe to a channel to receive the notification and to see this in the list of your channels. It means in principle, you need to press a plus, browse the channels, all the public channels you can subscribe to what you want. For example, this lecture, for example, the intro to QCD, for example, the social, for example, the seminars channel and stuff like that. So to cut things down and the possibility of misunderstanding, Malte will subscribe you to all the public channels, and you're free to unsubscribe yourself if they bother you. Okay, but he's gonna subscribe you automatically to everything possible available so far, and you're free to do whatever you want. But so don't be surprised if your phone starts pinging. Okay, I'm done.
okay, so according to my watch, it's 2:32, so you have 15 minutes.
Testing.
They were not.
Cool.
Welcome everyone again. Now we continue with the set of lectures from Arkaitz in the quest for Exotica.
Sorry.
It works. Okay. Yes, so we finished by taking a look at the business here, this moment. These are what I call the vector mesons. So they have unique angular momentum. I can also call it the same if you want. The idea is, in this lecture, we're going to take a bit, just a look at the quark model construction of these guys. I don't want to get into the details, because we are not going to do exercises predicting anything with the quark model, but the quantum numbers. So all I care about now is going to be defining quantum numbers that are going to give us possible strong decays. And then we will go into the case. So we saw the pseudoscalar meson effect. We saw where they are so light. And then I introduce you to the vector mesons. For example, this is how I would describe the quark construction of the pairs. Remember that I am just for convenience, for simplicity, not doing the second translation of these guys. But you will always see this, that you always have to synchronize. For simplicity, they most of the times never give you the full thing. And we're going to take a look at this and the way that they are built on the quark model. Remember, I don't care much about the details, and so I will just pass right through it. So let's start with a single quark. We have a lonely quark that has the spin components, then some spatial wave function, then the boring part and the color. And we're going to build, remember that our hadrons are color singlets, so that our part is going to go. We're not going to look at the color part of a quark anti-quark construction, but then it's going to have some basic quantum numbers. Again, this symmetrization or the symmetrization. The idea is that these basic quantum numbers, if I was to write in this horrible formula, I only care with you realizing that it's going to have some Klebskor times, which are the tables before, that are going to tell us how we build the total spin and angular momentum of the hadron by using the quarks. So the ones that we got from the table before, and then some wave function for the spatial component. Now we're going to write it in the spectroscopic notation. And the idea at the end of the day is that we can recover a formula like this, where we have some quark structure here with some symmetrization. This means, if you remember, if you don't, I have the formula here, that when we apply parity transformation here, and we are going to flip the wave functions now, we are going to recover a -1 to the L, depending on the angular momentum of the object. So whenever we have a hadron built by quarks, we will have the -1 to the L, depending on the angular momentum of this hadron. And then a +1, because particles of quarks and anti-quarks are opposite, right? So plus and minus is minus. So this +1 because we have quarks and anti-quarks. If we do that for charge conjugation flips the particle to its anti-particle, right? And so we're going to recover a -1 to the L for the angular momentum and another -1 to the L for the total spin. So the message to take home is, if we build mesons using a quark model, not all quantum numbers are allowed. If I am going to use JPC, so angular momentum, which we said is a fantastic quantum number, and then parity and charge conjugation to define our states, only some of them will exist in terms of the quark model. For example, for total spins, singlet means spin 0, triplet means spin 1. These are the quantum numbers that are allowed for JPC. So what would happen, can somebody tell me? And this is very important for us. So what could happen if on a triplet system, we determine an experiment a particle that exists in 1 minus plus quantum numbers. Polarity negative, charge conjugation positive, and then the total angular momentum is 1. Is it in this table? It's not in this table. So what is it? What is it made of? Well, certainly not quark anti-quark. Can somebody tell me, that's what people like to get the first time in. Can somebody tell me what is a 1 minus plus object? How do we call them? A hybrid meson. We will see what a hybrid meson is. Hybrid meson is a strong word here because a big chunk of the experimental program in this building is devoted to hybrid mesons. The detector upgrade Gluex is devoted to hybrid mesons, so we'll play with that. So now let's go back to something simple, the vector mesons. We had 9 here, and I just put it to this side, 3 of them. So let's say that JPC was everything there was, and these are all the quantum numbers we care about. Well, J and P for these 3 mesons are basically the same. This one doesn't have like a properly defined charge conjugation, but the other 2 have. So they are more or less the same in terms of this quantum number. But the quark and the quark construction is not the same. So wait, we are going to classify things from quantum numbers, and then we got the same quantum numbers, and then these 3 objects look massively different. This doesn't seem to be all there is to the, these particles, right? We are going to need something else. Well, first things first, let's check that everything works. So maybe the quark model doesn't. If we were to calculate the transition from an E plus E minus related through a photon to 2 quarks, and we do this for the rho 0, okay? Why the rho 0? Why not the rho plus? Because photons have no charge, so it must be rho 0. So if we do this for rho 0, then we get something that is proportional to this term, depending on the charges of the quarks. If we do it for a 5, for example, we will get a term like this. And if we do it for an omega 0, then we will get a term like this. So they should appear, or basically the decay should go in the ratio 9 to 1 to 2, when we do rho to omega to 5. What is the experimental data? Well, it's fantastic, right? Perfect within uncertainties. So yes, our model works. So we are missing something else. We need some more quantum numbers. If we, for example, determine the decay of the rho 0, it goes, and I'm telling you, to pi plus pi minus. This leg here is connected now through a gluon. So these are connected quark lines. This is its main decay mode. Will this decay into pi plus pi minus because it has the same JP? It cannot, because that's a strangeness. Will this decay into pi plus pi minus if it's neutral? Well, it will not, because there is something else, some other symmetry preventing it from decaying to 2 pi's. I mean, I never included the isospin in this list, but I was telling you that it was very relevant, and it's even in the title, right? So we better include it as a quantum number to describe our states. But what is this G? Can somebody tell me what is this G? So this is what we call G parity. And it will be very useful for some of these decays. You'll see, in particular, for things decaying to pions is, frankly speaking, trivial to realize, or very easy to realize to how many pions something can decay reducing the parity. So in order to define it, we're going to do some hand-wavy group theory because I'm not going to describe everything in detail, but I can give you quick books about that. So first things first, out of the 3 components of the isospin, the second one, y-axis, x, y, and z, the y-axis commutes with the charge conjugation rate. And we're going to use this. Now, the second thing that we're going to do is we're going to define a rotation of 180 degrees over the y-axis of isospin. So if we had this, our axis, this would be a 90 degrees rotation, right? We want 180 degrees. So basically, we are going to get the isospin sub x, and we're going to flip it to minus I sub x. We're going to get I sub c, and flip the sign. And this is what we get at the end of the day. Of course, the isospin in the y-axis remains invariant because we are rotating everything around the y-axis. So the isospin remains invariant. So we are going to build this operator, which is the charge conjugation times this rotation that we just did. And because charge conjugation and I sub y commute. And the rotation is just the exponential. At the end of the day, these things commute. Okay? So this is the G parity operator definition. And let's do an explicit example with pilots. If you go to the PDE, to the book, and then you look at the state, it's defined by isospin, G parity, and then J3C. And so it's minus. Let's calculate it. The rotation in terms of pions looks as matrix like this. So now we have a triplet, 3 pions. This rotation operator is a 3 times 3 matrix, right? And what does it do? What does it do? Okay. If we have a pi plus and we rotate the isospins of a pi plus, let's say that in this rotation we're flipping the third component of the isospin of a pi plus. Where does the pi plus go? It goes from pi minus, right? We flip the sign of the third component of isospin. So we went from +1 to -1. This is the pi minus. And then if we act with the charge conjugation operator on the pi minus, is minus the pi plus, with the usual definition of the convention of the charge operator. So we got a -1 sign, which is the one here. Also, for the pi 0, which is in the middle, right? The rotation in this definition is going to change the sign. So the rotation acting on pi 0 is going to give me minus pi 0. And now the charge conjugation over minus pi 0, well, it's going to give me minus pi 0 because the charge conjugation of a pi 0 is plus. So again, it gives me a -1 sign. So in summary, finding this operator this way, finding G parity this way, all the signs of this operator acting on a system that has well-defined parity, G parity, are the same. Or basically, if you have a multiplet with well-defined G parity, then the sign is the same on every element of the multiplet. This is why we define it this way. If you have like a well-defined isospin, like for example, an integer isospin, then you can prove that this is the following. And I won't do that. But I can lead you to the books that do it. So any question about this G parity operator? Or these quantum numbers that we're going to look at?
So you say you need 5 total to describe the pi knot perfectly. But if you go to like the previous slide, G is written already in terms of C and I. So would that mean that you only need 4 of these quantum numbers?
Oh, you mean this? Well, the thing is, as I said before, this always happens when you have a well-defined isospin that is an integer. There are objects that don't have well-defined G parity. So there are objects that won't have this number.
Okay.
So in principle, you put all the numbers that can classify all of them. And then some of them won't have G parity, for example, so it won't be a good number. But yeah, if you knew C and if you knew the isospin, then of course G parity is trivial. So the idea is that for some states it's very easy to see where they decay into with an isospin and G parity combination. And also because this only flips sign, I'm pretty sure that you could have systems, complicated systems, where different isospins give you the same sign for G parity, right? So it'll be kind of not redundant unless you have it right. Any other question?
Maybe a big picture question. How should we understand the success of the Porte model in describing the spectra, given that it also describes the proton, the total quantum numbers, but we know microscopically that the spin orbital angular momentum of the proton looks nothing like the Porte model. So is it getting the right answer for the wrong reasons? Is it expressing the right answer in a different way? How do you think about that?
Always. So first things first. Well, I don't really work on formal descriptions because I am not a heavy supporter of using it always in a spectroscopy or what we do. But it is true that, well, the idea is, if it was completely incorrect, then we couldn't be getting balanced pictures out of some hadrons. And so there would be this interrelation between being able to define a proton as 3 valence quarks and having a quark model that gives us something like that proton. I found always very interesting that it can predict some things like the masses of some hadrons, right? But then some other things like decay rates or some other properties are completely out of question by orders of magnitude. So it's not only for protons, it's also for mesons that something is well predicted by the core model, the Lattice pictures usually, but then everything that looks beyond that is horribly wrong. In this case, we are gonna use it only to motivate the states that do not have core model the quantum numbers. And also to motivate interaction of these quantum numbers. Yeah. Any other question? Any question online? So let's go into the case. So I introduced you to rho 0 decay to pi plus pi minus pi. Now, as I said, this guy has different, well, this guy has an isospin 1/2, so it doesn't have well-defined G part in this case. But because it has isospin 1/2, we can see what is decay, right? It could indicate to a certain number of pions, because it has like an integer number. So this would be 0, 1, 2. It has to have something with isospin 1/2, because it has a strangeness. It's going to decay mostly to pi, right? Makes sense. But now about the omega. The omega is a pure light. And in principle, you would think that it also decays to pions, right? But the G parity of the omega is not plus like rho. It's minus. So what does it mean? G parity is a multiplicative operator. So if you have 2 pions with G parity minus, then the total G parity of the system is plus. If you have 3 pions, then it's minus. So you see now it's so simple to see these kind of decay channels from particles that have well-defined G parity. Because if it's a negative number, then there will be an odd number of pions in the final state. If it's positive G parity, there will be an even number of pions in the final state. So it's telling you where to look for. And these guys are very interesting. So, for example, I introduced you before the fact that if you want to look beyond the standard model, and you want to, for example, describe the Hadron vacuum polarization to the anomalous magnetic moment of the muon, on this super long sentence, if you want to predict these red values that are very precise, you have to describe with utmost precision the rho and the omega line shapes. No way around that. It's the main contribution to this number here. So if you were at the end of the day to claim that exists beyond standard model physics, you better do a good job tackling this down. And the K star somehow enters the calculation of the decays in the fact that these are the meson decays of our processes. And in the middle, you have a final state of IK dominated by the K star. So you better get this one right. Now, problem is, we were talking before in the previous lecture about the distances that some objects travel, right? Well, these are the distances that these objects travel in the restaurant. So, if you are able to build a detector of the size of the travel distance of these guys, give us a call. Okay. The problem here is there is no way we can see these ones. They are not particles that live or they are stable through QCD. They decay through external interactions. And so they are called resonances because they are not stable. Now, how do we measure these guys? How do we determine them with precision? And so this is what we do here. These guys are going to decay to other particles. And so they leave tracks. So let's say that we are, I think this is, I don't know, this might be CLS or Atlas. So if we had 2 beams of particles colliding with each other, and then it was to produce a rho resonance at some point inside chamber, inside the calorimeter here, this will decay a very short distance. And then it will decay to 2 pions that go in opposite directions. Now, I detect those 2 pions, and a supercomputer counts all these hits. At the end of the day, can reconstruct the decay of this rho. And by studying the properties and the way these 2 pions were created, infer properties about this rho resonance. This is what we do in accelerators. Some particles are easy to detect than others. This depends on the design of the calorimeters, and we have experts working on that. And of course, as I said before, you have to have a right idea when building an experiment of which particles you want in the initial and which particles you want in the final states in order for all these to work. So as a summary, in accelerators, we get our particles, long-lived particles, we accelerate them to high energies, we smash them against a target or against each other, and then we produce lots of products that we are going to collect. So now, how is this related? to QCD, how is this related to amplitude analysis? The idea is the number of hits that we count are related to the probability of a given decay to be produced. This is quantum mechanics, quantum field, nothing new. So whatever we do here accelerated, at the end of the day, it looks like this in the data. And this is going to be related to our amplitudes, to these transition amplitudes, decay, processes, scattering, etc. So let's start by defining, again, my favorite variables, the Mandel subvariables. So if we have a process of 2 to 2, we can define these 3 variants. Let's say that particles have no spin. They are, let's say, 2 pions going to 2 pions. In that case, we can define just 3 particles and express or formulate everything in terms of just these simple variables. So this is going to be the S variable, which runs in this direction, is the invariant mass of the system. This basically is measuring the angle between P1 and P3, and this will be measuring the one between P1 and P4. Okay. Did somebody finish the exercise that I asked before? Okay. So we're going to define a transition amplitude. So this is going to be the S matrix. This is what I care about the most. Let's say that I have a system alpha in the initial state. I don't know what alpha is, but I know it's in the initial state. And then I have some collection of particles in the final state called beta. In the asymptotic time where they no longer interact, I collected some beta particles in my Hermite. So the transition from alpha initial state to beta, sandwiches between this S function, is called the S matrix, which is gonna encode everything that is happening for alpha to become beta. Okay? Now I don't have an algebraic expression for this in general, but I'm gonna describe this in terms of very basic first principles that the theory has presented. The first one, so once a wise man said, 100% of the times, quantum mechanics, something will happen. So you don't know this guy, but we do. And this translates into the unitarity equation, which means if you start with a system of particles, and then you collect the probability for this system of particles to decay to everything, and you collected all of them, theoretically you can do that, experimentally that's another question, then the probability must be 1, which means that this operator must be unitary. When you are calculating, for example, let's think about one single channel. This is a matrix, but let's think about one channel, I pi to pi pi, and only that can happen. Then this is a function, right? And a function times its complex conjugate is the modulus of the function. This is the total probability, which must be equal 1. So yes, unitarity is a basic principle. So we are going to adopt this. Now it's ours. Now we're going to define this S matrix as the identity plus something. Why? Because inside this S matrix there are many processes that can be encoded. One is the trivial non-interactive process. Let's say that I have 2 pions in the initial state, and they are too far apart. They don't see each other. And then I end up with 2 pions in the final state. Well, I don't really care about this reaction because nothing happened in the middle, and I want to study QCD interactions. So this identity, which is the trivial reaction, is going to be subtracted from this. So S minus 1 is what we want, the T matrix, the amplitude. Now, because this is unitary, you can do this as exercise. This is a unitary equation for T. And what we are going to prove in the next lectures, Friday, is the optical theorem. The idea is, as I promised before, we count the number of hits on the detector. And this is basically the total cross-section of a process. This is the total number of hits. And this, the optical theorem, can be related to the amplitude for a given set of one-dimensional variables. So yes, if we get this on an experiment, then we got this. And this is what we are hoping for. So let's start motivating the idea of resonances. First things first, once again, remember, angular momentum is conserved. It's a fantastic quantum number. So we can get the amplitude T, capital T, and then we can split it in different angular momentums. It's what we call the Parseval expansion. So what we are doing, all we are doing is basically extracting the orbital angular momentum part, and then we will have Parsevals inside that have some different values, of course, depending on the energies. And these guys have well-defined angular momentum. Okay, so let's take a look at quantum mechanics. if we have a system that is an eigenstate of the Hamiltonian, we have a system that lives forever, right? Because if we solve the Schrodinger equation, then we know that the evolution is e to the minus I times ht. It's an eigenstate now. So this h is just going to be the mass of the state. So this thing is oscillating over time, which means that the probability of finding it never decreases. It lives forever. And this is what we call a bound state. Do you know examples of bound states in strong interactions? Protons. There is one very interesting. The deuteron. Do you guys know the deuteron? The deuteron is a bound state. It lives forever. There are strong interactions. It is created by two nucleons interacting with each other. So this is kind of the wave function for this kind of objects. But what happens with a quasi-eigenstate? This hand wave appear. So now this energy is no longer real. It has some imaginary part because it's not fully an eigenstate. As we multiply with I, you get a term that is real. I am writing it this way, so we see what happens. If I get the probability for this state to live at a given time t, then we see that this thing is fading away. So the probability of finding that state at a time t is decaying with an exponential. What's happening? I mean, the state is disappearing, is decaying, right? If you go to times t infinite, then there is no probability to find it. We say that usually it lives for 1 over gamma, is the suppression 1 over e, right? Which is a kind of a standard definition of the lifetime of something. So if you go get this amplitude, remember, this was quantum mechanics. We are in relativistic description, but if you go on to a Fourier transfer of this to change from the t variable to the energy, okay, that is going to be our x-axis, then this kind of exponentials end up being what? They always end up being, the exponents end up being part of our denominators. Okay, so this is almost a pole. If it didn't have this gamma, it would be a pole on the real axis. Because it has a gamma, it's now a pole where? On the complex plane, right? If E is m minus this part, then it's a pole. So experiments are run in the real axis, not start. But the idea is very close by to this real axis where we measure things, we can have poles. And these are going to create peaks in our amplitudes. Because very close to where we are measuring in front of it, we have a huge pole. So we are cutting part of a mountain, right? And this is what we see in the amplitude. Okay, so what is this? This was the interaction to the light spectrum. So these are different colors, bunch of peaks, green, red, whatever it is. What is this? That is the Higgs boson. I mean, it was an incredibly challenging definition, but basically determination and construction of the accelerator and everything that gave birth to the measurement. But from the amplitude analysis point of view, this is as trivial as it gets. It cannot get any simpler than a bright linear formula, which is what we are giving you now. It means it's isolated, it has a very nice peak, and it's a simple resonance. So it's a pole in the complex plane, very close to the real axis where it's measured. Okay? And with that, by fitting this data, we can determine its mass and its decay width, or basically the inverse of its lifetime, right? Now, how does it look for us in hydrophysics? Let's say that we have, as I said before, pi to pi, so it's elastic. In the elastic region, the amplitude will be described with a modulus and a phase. That's all there is to a complex function. So the modulus will look like this formula, like the Higgs. And the phase will look like this rapid phase motion that we have in the plot to the right. This is the relativistic gradient formula. Okay, so we have a toolkit to fit things and to describe it, right? And for many, many years, this was a very successful tool to hadron spectroscopy. You have lots of different peaks that can be well described by this formula. And so you can extract all these levels in the spectrum, its masses and its widths. However, light is not so simple. Many other reactions, particularly the ones that we are looking at nowadays, are much more challenging. So whereas you can look at things like this and describe them with brightness for the rho that we've been talking about, getting its excitations, like the rho prime, is not so simple. And these formulas break. What happens if we do, for example, 3-particle decays? Everything I did was 2 particles to 2 particles, but QCD doesn't prevent us from having 1,000 particles in the phase. So what happens if I go and look at 3 particles in the phase? Well, we don't really have the formalized that we're just started to apply. Or what happens if we look at non-trivial structures, like the lambda 1405, a resonance that is apparently 2 poles almost together. This is definitely not driving a resonance, right? What happens with the simplest, lightest scalar meson nonet? So I introduce you the pions, kaons, etc., and vector mesons. What happens? These guys are very closely related to the vector mesons. They are produced in pipe interactions, bike interactions, and they are like the vector mesons, like the rho and omega that I introduced before, only they don't have angular momentum. The angular momentum is 0. Well, does this guy look like the peaks that I was describing before? Does this one look like that? Is this peak a broadly safe and smooth, like the one I showed you before? No. None of these can be described in this formula. So there are many questions about how to do this. Basically, we got to a bypass where our formula broke. Do you know how to solve everything? Yeah.
Oh, I have a question. I don't know how to solve it. Maybe this is kind of what you were getting at, but is there a technical difference between a particle and a resonance?
Well, so a particle, for example, particle like a kaon, that's in the decay under the strong interaction, right? It's a stable particle under the QCD. But it decays under the electroweak reaction, right? So it has some lifetime. So in that sense, kaon is a stable particle in QCD, but it's a resonance in electroweak reactions. It's just here we are forgetting, because strong interactions dominate everything, we are forgetting about electroweak and electromagnetic decays. We are only caring about what happens in QCD, because we are studying QCD. But for example, I'm not going to go back to the previous PDF that I had from the first lecture, but if you remember KS and KL, K-long and K-short, are eigenstates of the Hamilton, right? And they have well-defined CP numbers and everything, and we looked at the mixing and evolution of a K-short. You remember that there were some parameters on the probability equation that are the gamma S and gamma L, because they decay according to wave processes.
Particle decays under a given interaction. It's a resonance.
It's no longer stable.
It's a resonance in that interaction. If not, it's a.
Indeed, well, at least it's a particle. All of them are particles, but it's a stable or not stable. So under QCD, these guys we're talking about the pions and the kaons are stable, but they are not stable. For example, IC is not stable under the electromagnetic force, right?
So like a neutron is a resonance for the weak interaction.
Well, yes, if it decays, yes, then it has some lifetime, and then you can call it a resonance because you can associate it with a mass and then a lifetime. So at some point, the propagator of that particle, propagator in the denominator part, is not on the real axis. It must be a bit deeper into the context.
So you talked about detector and how we measure the decay products and not the resonances, right? Because they're short-lived.
Yes.
Now, if let's say there are 2 resonances who have the same decay products, how do you differentiate between one being?
Oh, that's a very interesting question. So unfortunately, that's a very complicated one to answer. But usually, what happens when 2 resonances decay to the same products, right, is let's take a look. This is gonna make it simple. So, can I see? Like for example here. So here you have 2 resonances, epsilon resonances that decay to the same products. This is the same environment. I don't think you see much because it's a horrible low resolution plot, sorry about that, but you see this thing, right? And then you see the second one, which is an excitation. And you can tackle them down because it's narrow enough. So in the environment, you show first one, then some space, and then the second one. Also in the energy, the variables that you can determine in your experiment, they didn't show up on top of each other. The resolution in the energy because they have different parameters, make them split apart, right? Yeah, indeed, I mean, the momentum is different. They show up at different energies. So they show up at different momentums. So if you are doing everything in terms of the phase space of momentum, then they show up at different points in the energy. And so you can tell me, you know, this is the ground state of this family, this is the excitation of this one. But it can happen, and we will explore it in the next lectures on Friday, that some of these overlap, like a big overlap, and then things get much more challenging. But this is what we are, well, where we are heading to partially. Okay, so let me continue because I still have to finish this part. So let's say that this was all too complicated. We don't like it, and we are tired because it's the afternoon. So we're just going to move on. We are no longer going to look at experiments, and we're going to go into the Lattice Qcd mode. Lattice Qcd is a numerical approach to solving QCD. So instead of measuring a detector and everything, we're going to use a supercomputer. And what we are going to do is our space-time is not going to be a box. Okay? A discretized box. So you're going to have some points, some space-time points. So the good thing about this is that it's non-perturbative, so we don't have to fight against, you know, things that don't want to converge because they are not friendly to us. And it's systematically improved. So we can make our boxes bigger and our spaces, basically our grids, finer. So less coarse. Now we have to do a collection of steps. And I am not going to look into, well, basically, we're not going to go into detail because all I'm trying to use Lattice Qcd for is a motivation to amplitude analysis. But let's take a look at this. So in Lattice Qcd, what we want to calculate is called correlation function, like this. This is the birth textbook definition. So if you open a book on QFT and you look for a correlation function, this is how it looks like. There's nothing new here for Lattice Qcd. And the thing is, 2 in the Feynman formulation, that you will have to sum over all possible paths in the continuum, right? But in Lattice Qcd, all these integrals become multidimensional integrals on each one of these possible points in the lattice. Here you have 4. It will be a 4-dimensional integral. For this variable must be integrated over all possible values the field can get at this point. Okay? We're going to have multidimensional integrals, huge multidimensional integrals, and we are hoping to solve the numerical. Well, what is the path of Lattice Qcd? Well, the path is that if you were looking at these correlation functions, then this is a highly oscillatory, like terribly highly oscillatory. So have you ever tried to integrate something that oscillates super fast? And you know how much precision do you need for this? Yeah, you can always like answer the keyboard and try to do it, but yeah, it doesn't really work, right? The second one is that you need to do, I mean, how high of a high dimensional integral have you performed by hand? Like a 3-dimensional integral? Well, for an ordinary lattice size nowadays, you will need, roughly speaking, a 20 million dimensional integral, something like that. Yeah, I've never solved one of those. So we are going to go in kind of like different way, like perpendicular to this. And we're going to define imaginary time because we can. So I times S, so I times the action, is going to become just minus the Euclidean action. Okay? And now, if we do that, well, of course, the temporal variable is kind of a space-like now. So we went from Minkowski spacetime to Euclidean spacetime. Fine. The second thing is, for the partition function, which is, again, textbook definition, looks like this. We can, first things first, if you don't remember, I tell you, we can perform algebraically the fermion integral. So there are some variables, then we get this action, and we split the fermion part plus the gluon part. And then there's some variables integral over there with the fermion action. This is the determinant of what we call the direct functions. Okay? And you can perform algebraically because they are Grassmann variables. And now the second part is the gluon, basically the gluon action. There's a minus sign with the exponential. So this is bounded. It's like probability line, right? It's between 0 and 1 because that is a real number. Okay, let's keep going with this probability thing. Let's see what we can make. So how do you perform integrals? You usually solve them algebraically, right? How do you perform the integral of 1 between A and B? Well, that is B minus A. If you normalize it, then it's 1. But what if I want to perform integrals by averaging values? Because I don't know how to perform integrals. So what is the average of 1 if I sample many times? What is the average of 1 if I sample 100 times? It's 1. If I sample 1,000 times, it's 1. So the integral of 1 and the sample and average over 1 is the same. What happens if I sample x here? Let's say that I integrate x between 0 and 1. What is the integral of x between 0 and 1? It's x squared divided by 2. Between 0 and 1, it means 1/2, right? If I sample uniformly, this is important, between 0 and 1, and I have one average, what is the average? So let's say I have 2 points. One is at 0, the other one is at 1, and I have the average. It's 1/2. Let's say I sample 1,000,000 times, and so I have a continuous uniform distribution of points between 0 and 1, and I average that. What's the value of that? It's 1/2, right? So again, integrals can be calculated as the limit of an average sampling. If you know the probability distribution, you should be sampling accordingly. So this multi-million integral, actually this part, these U are the gluons, part of the fermions, we did algebraic. So we are not going to calculate this millionth dimensional integral. What we're going to do is sample our observables and do averages. So we no longer have to do a million dimensional integral. Yes?
Do you have to be concerned about the loss of information due to the fact that you cannot completely define an arbitrary distribution by its elements?
So the idea is that the probability distribution, you can calculate, you know the explicit formula for the probability distribution. So it's about getting it right. It's not that you have to infer it or build something generic. You know the probability distribution. It's this one. I'm giving it to you. It's this one. So you know it algebraically. Now the problem is on you to produce an algorithm that calculates on every gluon link. So on every one of these values for the links that are distributed according to this distribution. So that is on you to do, and we are not going to go that way. There are tons of algorithms. Some better than others. They usually take you lots of time, but at the end of the day you can get something. And indeed, you have some uncertainty associated with that. So Lattice Qcd doesn't give you a value. It gives you a value with a measured error, hoping to estimate all these errors properly. So now our observables are samples according to, some probability distribution of these links, and then we are just going to do an average. Usually, probably, if we want something good, thousands of average, right? So we have to sample thousands of times the gluon picture. So the idea is we care about mesons, so we better calculate on our observables a quark anti-quark system, because mesons are built of quark anti-quarks, right? So unless we calculate them on the lattice, then we are not going to be able to calculate mesons. So this horrible integral, again, you can split the fermion and the gluon parts of the integral. This is the gluon part of the integral, and this is how the fermion part looks like. If I didn't have this quark anti-quark part, this would be again just like the determinant that we did before. But now we have this quark anti-quark. So this ends up being this d minus 1, which is the inverse of what they call the Dirac matrix. Now, the last step, this integral, once again, is just now sampling over pictures of you with a given probability distribution that is complicated to get and very expensive, but we can do it. So we got our basic building block. It's a huge basic building block, because remember, it's connecting points in the lattice, every point in the lattice. This can be millions, and this can be millions. Okay? So it's a huge matrix. Oh, sorry. This is usually around 100,000. So it's a huge matrix. So now the idea is that when doing these propagators, we can build patterns. What is the definition of pattern? As I said before, is UD bar. Okay, the explicit one includes a gamma 5 inside, because can somebody tell me why is a gamma 5 in my pattern and not a gamma 4? Indeed, because the parity is negative, so it must have a gamma 5. So this is my pattern, and this is my pattern. And the contraction at the end of the day basically we get the D bar with the D part, and then we get the U with the U bar. And this is how we pictorially, well, this is a very ugly plot, but this is how we pictorially describe contracting a path in the lattice. Okay, so we did all this, we got our clever algorithms, and then at the end of the day, we got the evolution of these operators on the lattice for pi. Why do we care about that? The thing is, we no longer have Hamiltonian evolution, right? We went to imaginary time. So this exponent is now a decaying exponential. And those energies, because they are decaying exponential, we can fit very well. So when I put a system of particles here, let's say pions and excitations of pions, I end up recovering lots of these. As many as systems I put here for the basis, okay? So I can get this on lattice, and this is actually a result with the error bars. So you see the energy is a value, central value, and it has some error bar that probably the people in the back don't see, but I promise you there is some error bar over there. So why are these energies relevant for us? I mean, okay, fine. You want these energies? What are they? Good thing is we can relate them to the continuous Minkowski spacetime world by just realizing that this box had some periodic boundary conditions, right? It wasn't an infinite box. So in order for everything to work, I had to define some periodic boundary conditions. And let's start with a one-dimensional example. I get two pions and I put them on a plane wave and I throw them into the box, like one-dimensional box at 0. So it looks like this, into the I get 0. And then at some point they interact inside the box and they go all the way to the end. So at the end of the box, what we get is I keep L, right, inside some box, plus something. This something measures the interaction between these two pions. This is called the phase, right? Now, because I have boundary conditions and I define this ordinary ones, the simplest case, we recover a quantization condition. You probably have done in quantum mechanics exercises like this with explicit basis or without interaction, so you get the quantized levels. These Kn are the quantized levels in the box. These Kn are the energies we are determining in the box. These are the quantized levels in the box. So what is this equation at the end of the day? This is an equation that tells me what the phase looks like if I give you the quantized levels in the box, which I just calculated. So what this equation, and now it's cut by Zoom, what this is telling me? It's telling me that if I calculate the energies, they become, it's okay, so if I calculate the energies, they become the x-axis on my equation, right? This delta is defined with Kn in mind. So Kn is the x-axis. So I calculated this result from the computer, the supercomputer, and then I'm going to just flip it over. It becomes my x-axis now. And wherever I have one of these, like this equation, we will have a value for delta. Using this point and that. So why did we just do? We went full circle. So we didn't want to do the experiment because it was very complicated. We went the Lattice Qcd route, and then we arrived at a very simple. For a summary, regardless of if you work with a super accelerator or a supercomputer, you have common grounds. You must do what we call amplitude analysis. And here, we are going to impose very basic principles to extract the observables that we want to get into QCD or other possible processes. So I had a few slides to motivate the next set of lectures, but I'll stop here. So any questions?
Yeah, let me remind our remote audience that you can also make questions. You can raise your hand in Zoom or type it in the chat. So after a reminder, please go ahead if there are any questions in the room.
Yes, please.
Can you guarantee that you can always whip rotate?
No, not myself. But in principle, it's something that doesn't seem to be terribly problematic. But as I said, I mean, I don't know of like full proof of that.
More questions? Yeah, there.
So was the purpose of using imaginary time in Lattice Qcd to turn the oscillations into exponential growth or decay?
Indeed, it's just to turn highly oscillatory integrals into something bound by probability, so we can sample with averages over probability distributions.
Going back to resonance weights.
Yep.
When I look through the PDG, for example, the branching ratios for decaying mesons are quoted in terms of these right-Wigner weights. But I also have been told to understand those branching ratios as a relative probability of those decays occurring. And so does that mean it's guaranteed that the sum of the branching ratio, the sum of the widths is equal to the width of the original particle to give you a unity probability?
Yes, indeed, it should be. I mean, you are going to have some missing for all the possible reactions, electromagnetic and electroweak, but that is always going to be totally negligible. So the sum of all the branching fractions for different channels will always amount to the total branching fractions, to the total width of a meson. Otherwise, then you are violating unitarity. If you think in terms, probably just of what you asked, you know the K-matrix approach, we will introduce on Friday. But if you think in terms of the K-matrix, and then all these branching fractions don't amount to total width, then you can easily see that you are just violating this unitarity principle.
You are next, I think.
I haven't really thought about this much, but how, when you wick rotate and you relate the generating function to the partition function, how are the thermodynamic quantities that you can extract from that related to analogous form factors that describe similar quantities? Like,
So when you wick rotate, naively speaking, not all quantities that you calculate on your Euclidean action now are trivially related to Minkowski spacetime. Well, there's actually a few papers proving that. So not everything you calculate on the Euclidean wall now on the lattice can be one-to-one related to the infinite Minkowski spacetime. So there are many things that you have to be careful of. For example, these amplitudes, these correlation functions are not trivially related, these energies are not trivially related to our amplitudes. We did this quantization condition, which is a simplified version of the actual Lucier method, which is much more complicated. So there's no trivial relation in general. There are some other quantities that can be related trivially. And also, as a kind of summary, when you wick rotate, you are changing from your QFT to a statistical theory. You have a partition function, and then you have these lattices usually have a defined temperature because of the finite total time extension. And there are some things that you can calculate that are related to statistics on these lattices. There are some others, like for example, introducing some chemical potentials that are very challenging because they induce some other problems. But yeah, you are related QFT and statistical theory will be that.
More questions?
Any more questions? If not, I'm going to go into my 3 slides. No equations.
Okay,
If you
sure.
guys want. Fine. So, yes, to introduce you things that we've been talking about. So these are some examples. We have again the full list of Mesons. This is QCD, even that's all of this. And this is what we've been talking about today. But there are many more that can happen, right? We could have tetraquarks. We have a pair of quarks with a pair of antiquarks. We could have what we call molecule-like components. So for example, 2 pions bound together, mediated by remanence of the force, right? Principle that also happens in nuclei. We can have hybrids, and this is what a hybrid looks like in the valence picture. So quark, antiquark, and a gluon in the middle. And then we can also have the beautiful Bataglia plot gluon, which is an object just made of glue, right? Gluons can interact with themselves. So in the vacuum quantum numbers, we can have these kind of objects. And we do see states that resemble them experimentally. It's not that they are hidden. You don't see anything there, but I promise you there is a state called the 1710. Interesting thing, for example, about this state is this is one of these knowledge that we've been talking about, right? That I've been introducing to you. All these beloved knowledge that allow us to classify states. This is what the quark model predicts as a knowledge. But there is an extra state, this one. There should be only 9, but there's a 10th one with more or less that mass. What is that gap? It must be something else. It cannot be a quark model prediction, because it's not. So this guy, the global, we'll talk about that. What happens with the states that don't have these quantum numbers that we were speaking before? What happens with this 1 minus plus hybrid thing? Well, the picture is even more complicated, because if you do lattice Qcd calculations, you expect 1 to exist. But then you go to the PDG, and it seems like there exists 2, and no theoretical prediction ever predicted 2. So we're seriously misunderstanding something. It's this like both hybrids. We'll talk about that. And now we won't talk about the huge plethora of possible exotics that you can look at these quantum numbers. Many of these states are not described in this table. And these are all in Charmonian. These are basically most of them Charmonian mesons. So X, Y, Z. And we have a program to study that in the future here at Jefferson Lab. So, well, stay tuned tomorrow morning, Friday morning. We will talk about these exotics.
Very much, Arkaitz. So now this is followed by an informal discussion that should go until 4:15, we'd say. And we can be not that strict with that. And then at 4:30 we have the social. So it's an open space for more questions or discussion,